Hello, physics students. Now you might be wondering what you're doing on the ceiling of my classroom. You're here to observe the Standing Waves lab. Now at this point, you should have already printed out all the pages of the lab write-up in the Google Classroom stream. You'll need all the pages to draw diagrams, enter your data, do calculations, and answer questions. Now obviously we're going to begin with part one, but right away we run into a little bit of a problem because I don't have a lab partner here. Well, you're my lab partner, but you're not physically here, you're only here in spirit. And what I have to do is set up waves that go on opposite ends of a spring so we could observe constructive and destructive interference. So as you can see, I've got my spring here that you saw in the video lesson on standing waves, and I could send one wave on this end, but again, there's only a table on the other end holding the leg, so I can't send the two simultaneous pulses required. So what we're going to do is we're just going to work through part one just based on what you know about interference without actually seeing the interference happen. So let's, I'll move the camera and I'll help you and guide you through the diagrams of part one. So imagine I had a lab partner and I shook and maybe waved my hand to the top of the screen, my partner toward the top of the screen, and we created two identical waves. Notice that the waves are one box high and they fit within one box horizontally, both of them. They should be exactly the same wave. What I want you to do is draw what happens to the rope or the spring when the waves are in the middle. So this is the equilibrium position. When the two waves overlap, say it was happening right here, what would you see on the spring at that time? You're going to be graded for the accuracy of the height and the width of your resulting wave. So go ahead and sketch that now. And then, after the waves pass each other, suppose you snapped a picture a little time later, like if this took half of a second for them to meet, what would the spring look like a half of a second after that, after they met? Draw the waves, the spring here. Again, you're going to be graded on all heights and widths of all waves that you draw. So go ahead and do that now. Okay, then the next thing, suppose that when I shook toward the top of the screen, my lab partner shook toward the bottom of the screen, and now these waves are going to come and meet somewhere in the middle. Draw what the spring would look like if you snapped a photo of the two waves when they perfectly overlapped. Do that here. Again, you're going to be graded on heights and widths, your accuracy of the resulting wave. So go ahead and sketch that now. And then let's suppose they took half of a second to meet. A half of a second after they met, what would the spring look like based on these two original waves? Again, you're graded on height and width of the any resulting waves that you draw. So go ahead and sketch that now. All right, so now we're going to move on to part two, and what we're going to do in part two is what I call preliminary data. What we're going to be doing is figuring out the speed of waves on this spring. Now remember, the speed of a wave is not affected by the amplitude of the wave or the frequency of the wave. For example, sound, if you look it up on the reference table, the speed of sound at STP is 331 meters a second. That's the same speed whether a bird is chirping or a lion is roaring. High-pitched, low-pitched, high-frequency, low-frequency, doesn't matter. It doesn't matter if the bird is chirping very loudly or very quietly. The amplitude doesn't affect the speed. It's 331. Same thing with light. It's 3 times 10 to the 8th, no matter what color or frequency the light is oscillating at. So what I'm going to do is throughout the lab, I'm going to figure out first the speed of the wave on that spring, and then it's going to be the same throughout the lab. No matter how I shake the spring, it'll have the waves will have the same speed. Now, in order to determine the speed, as you can see from your lab sheet, I need to determine the total distance and the total time that a wave travels along a spring. So for the distance, what I'm going to do is I'm going to use a tape measure to measure the length of my spring. I'm going to stretch it from here. This is the beginning of the spring. And the end is going to be over here. So what I see, 3 meters here, I see about 3.60 meters for the length of my spring. Of course, as always, you're going to have to retrieve your own data for the length of the spring. Now, I'm not going to write that in for the total distance. I'll explain why in a minute. It'll become clear. What I'm going to do now is create a wave pulse and time how long it takes to go on the spring, and I'll have distance and time, which will allow me to calculate the speed of the wave. So let me move the tape measure out of the way. Okay, and free the spring. Now the problem with my little experiment is when I go like this, it's so little time to go from one end of the spring to the other that, again, the stopwatch that I'm going to use is very inaccurate. So what I'm going to do is I'm going to let the wave bounce back and forth and time it as it's bouncing back and forth to increase the time and therefore improve the precision of my measurement. So I'll send a pulse and we'll watch how many times it reflects back and forth. Ready, set, go. Oops, I messed up. Let me try again. Okay. Ready, set, go. Okay, there it is. I got about 3.76 seconds. Let me secure the end of the spring so it doesn't fly across the room. Okay. So I wrote that down. Let's now take a look and see how we can use that time to figure out the speed. Now keep in mind, I didn't time it, like I said, just there. It went, if you go back and watch the video, the wave went forward, backwards, forward, backwards, forward, backwards. And then I stopped timing. So let's, I'll reconfigure the camera so I could show you how to calculate the speed from that data. So here's the data I just measured, 3.76 seconds, and the length of the spring, 3.6 meters. Again, you're getting your own data. But I left this blank because, remember I just said that I sent a wave pulse that went like this, reflected back and came back to me. Then reflected off my hand and came back. Reflected off my hand, reflected off the desk and came back. So it went this total distance, and remember the length of the spring is 3.6 meters. So what's the length for all of these, the total length that the wave pulse went for all those reflections? Figure that out and fill that in here. Go ahead and do that now. All right, now we've got a distance, we've got a time. There's a formula for speed on the reference table with distance and time. What I want you to do is look up the formula on the reference table. Again, at this point, you should be able to find all these formulas. So I'm not going to tell you where it is. Find the appropriate formula and calculate the speed. When remember, you got to have 3 steps here: formula, numbers, answer, and units everywhere. So go ahead and do that calculation now. Now I'm going to set up the first harmonic. And what I'm going to do is I'm going to get it vibrating, and what I want you to do is at some point when it reaches maximum amplitude, I want you to pause the video yourself. I won't tell you when because it's going to be awkward with the timing. Pause the video and note what the spring looks like when it's at maximum displacement, because you're going to sketch that later. And then what I'm going to do is I'm going to figure out the frequency of that standing wave in the first harmonic. And I'll do that by, again, timing the wave oscillations with the stopwatch. So that's basically what I'm going to do. So let me free the end of the spring here. And just a reminder, just so you know and you remember, the first harmonic looks like this. All right? If I shake faster, the second harmonic looks like this. If I shake faster still, the third harmonic looks like this. Each time I have more and more antinodes. I could make the fourth, the fifth, the sixth, but we're not going to do that in this lab. We're just going to study the first harmonic, the second harmonic, and the third harmonic. So again, here's the first harmonic. Pause the video yourself so that you can note what it looks like at maximum displacement, like maybe when it's all the way at the top of the screen. All right, now what I'm going to do is I'm going to time 10 oscillations. But remember, an oscillation is not like this. This is the wrong way to count. Start. 1, 2, 3, 4, 5, 6, 7. That's the wrong way. The right way is a complete cycle. So let's suppose I start when the spring is at the top of the screen. Start. 1, 2, 3, like that. And I'm going to time 10 oscillations. So ready, set, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I got a time. Let me secure this. Okay, so I'm going to write down my time of 12.64 seconds. And then let's go to the other view so I could help you through the calculations and the analysis of the first harmonic. So I decided to go ahead and calculate the speed based on my data. So just so, kind of grounds our calculations later, I'll be using this for all three harmonics. You'll have a different number, but you'll be using this same number for all three harmonics throughout our calculations. So what we just measured, or what I just measured, was the time that it took for 10 vibrations. 12.64 seconds. Now, again, that's the time for 10 oscillations. So what you want to do is convert this to the time for one oscillation. So you're going to get your data from Google Stream, and you're going to want to convert that to the time for one oscillation. Record that here. Go ahead and do that now. Okay, now, what I'm going to do is take you through this procedure. I kind of skipped ahead because of the way, we're going with this lab with the video camera. It was convenient to do step 4. But let me just say and warn you that there's a lot of steps here. And you got to make sure you do all of them. Like, for example, step 1, sketch the spring at maximum amplitude. So I created a freeze frame. If you don't remember what that looked like in the first harmonic, go back in the video and watch and see what that looks like. Sketch the spring if you were to snap a photo of it from above at maximum amplitude. Go ahead and do that now. All right, now step 2. Label the nodes with all nodes with N, all antinodes with AN, the wavelength with lambda, and the amplitude with A. And a lot of students, let me just again warn you, a lot of students skip this step. And if you do that, you don't label this diagram with all the nodes, antinodes, amplitude, and wavelength, you'll lose 4 points right here, -4. And then you'll lose 4 points in the second harmonic and 4 points in the third harmonic, which means you lose a total of 12 points for not labeling your waves. The lab is only worth 56 points. If you lose 12 points, you're in the C already. You're getting a C on the lab. Do not skip this step. Label all nodes, antinodes, wavelength, amplitude. By the way, in this case, it's easier to label what 1/2 of a wavelength is. So with lines, circle what part of the wave is equal to 1/2 of a wavelength. Go ahead, make all these labels now. Okay, the next step 3 use your sketch to determine the wavelength of the standing wave. So what you want to do is note that the length of your spring is a certain number of meters. Mine was 3.6 meters. And then, based on this diagram or your notes, figure out what the wavelength is. You don't have to write a formula, but what I want you to do is show how you calculated the wavelength. For example, if you think it's 3.6 meters divided by 3, it's not. But if you think that's the case, then this is how you would show your calculation. But you're going to figure out, based on your spring length and what you're doing to that to figure out the wavelength, go ahead and calculate the wavelength now. All right, the next step, time 10 cycles and determine the frequency from this measurement. So frequency is F. This here is capital T. There's a formula on the reference table. I'm not going to tell you where it is, but it tells you how to calculate the frequency from the period or the period from the frequency. Whatever the formula is, write it out. And then when you're all done, you're going to have the frequency with some number of hertz over here, or I shouldn't say the unit. You figure out the unit. So 2 steps, or actually maybe you could cram in 3 steps here. Go ahead and figure out the frequency based on this measurement now. All right, step number 5. The frequency using the V lambda F equation. There is a formula on the reference table that relates these 3 variables. What I want you to do is write out that formula over here. Plug in the data. You have V from the first page of the lab. So this is from page 1, the preliminary data. You got the speed of the wave. The wavelength is right here. And you're solving for F. So when you're all done, you're not using this F. You're calculating what it should be based on this equation and the speed and this wavelength. Go ahead and calculate the other frequency. Should be the same, but go ahead and calculate the frequency based on that equation now. And the last thing you're going to do is calculate a percent error. Here you don't have to write out a formula. So this is the theoretical value based on physics equation. This is the experimental. I'll just put EXP. So theoretical minus experimental over theoretical times 100%. Again, you don't have to write the formula out. You just have to plug in the numbers and then report what the percent error is. So go ahead and do that calculation now. All right, time for the second harmonic. So I'm going to set the harmonic up. Then I decided that maybe I will make a freeze frame so you could see what it looks like, so you'll be able to sketch it. And then I'm going to time the oscillations so I could measure the frequency of oscillation. So let's begin. Let me release the end of the spring here and shake in the second harmonic. All right, here it is. So now I'll freeze the frame so you could see what it looks like in a still image. And now I'm going to time 10 oscillations so we can measure what the frequency is from that 10 oscillations. So again, I'll start when this anti-note is at the top of the screen. Ready, set, go. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I got a time. Let me secure the end of the spring here. Okay, I got 5.87. Let me write that down. Again, you'll get your own time for 10 oscillations and use that for your analysis. So now let me reconfigure the camera so I can help you through the analysis of the second harmonic. All right, so I'm going to jump ahead again to step 4 here because I already measured the time on the floor over there. So this is the time for 10 vibrations. Again, you're going to look up your own time for 10 vibrations in the Google stream, but from this, you're going to figure out the time for 1 vibration and record it here. So go ahead and do that now. Okay, so let's now go back to step 1. sketch the spring at maximum amplitude right here. A beginning spring, end of spring. And again, if you don't remember what that looks like, go back in the video or your notes and look at what this the second harmonic looks like. Go ahead and sketch that now. Once again, this important step 2 that you could lose 4 points on if you skip, label all the nodes, all the antinodes, the wavelength, and the amplitude in this picture here. Go ahead and label those now. All right, step 3, use the sketch to determine the wavelength of your standing wave. So again, my wave was 3.6 meters long. Maybe I think that to find the wavelength, I divide by pi. Obviously, I don't. Or maybe this time I'll say I multiply by pi, right? Okay, so obviously that's not correct. But whatever you're doing with the 3.6 meters, the length of your spring that you were assigned, do that, show what you're doing, and then report the wavelength in that box. Go ahead and do that now. Okay, so the frequency from the stopwatch. So again, you've got a period here. This is the period. There's a formula that relates frequency and period. So go ahead and write that here, the formula, plug in the numbers, and then have your answer for frequency. Go ahead and calculate the frequency based on this time here. Go ahead and do that now. Once again, we're going to now calculate the frequency again and see how it compares to this experimental value. So we have to find a formula between these three, or among these three variables. It's on the reference table. I'm not going to tell you where. Find that formula. Write it down here. Something equals something. This is from page 1 again. The first page, the preliminary data. This is the wavelength we just determined right here. And you solve for the frequency. When you're all done, you plug in your numbers and you're going to get another frequency, hopefully that's the same as this or at least close. This is the theoretical value. So go ahead and make that calculation now. And percent error, once again, you're going to do the absolute value of the theoretical value minus the experimental value over the theoretical value times 100%. Again, no need to write a formula, just plug these numbers directly in here and then put the answer as a percent. So go ahead and make that calculation now. So we have one more analysis to go with the third harmonic. Again, I'm going to set up the oscillations, create a freeze frame, and then measure the time for 10 oscillations so we could get the measured frequency. So give me a moment to free the end of the spring. All right, third harmonic, here it is. All right, so what I'm going to do is, again, create a freeze frame so you could see what you're going to be sketching later. And then what I'm going to do is time 10 oscillations. When this antinode gets to the top, I'm going to time 10 vibrations. Ready, set, go. 2, 3. I think I messed up, so I'll try again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4.53. I might have messed up again. It's pretty tricky to do it. Let me try one more time. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, 4.49. I think that's going to be good enough for our measurements. Okay. So I got 4.49. Again, you're going to get your own value from the Google Stream. So let me reconfigure the camera. I'll help you through the analysis of the third harmonic. So this was my time, 4.49 seconds. Again, you'll get your time for 10 vibrations in the Google Stream. And from that time for 10 vibrations, you're going to find the time for one vibration. In other words, the period of that wave. So go ahead and do that now. Let's go back to step 1. You're going to sketch what the spring looks like over here. as if you took a photo from up above. If you're not sure, go back in the video, look at it, or go back in your notes and look at what the third harmonic looks like when you snap a still of it. So go ahead and sketch that now. Step 2, that crucial step that you don't want to skip because then you'll lose 4 points. You want to label all the nodes with N, all the antinodes with AN. Circle or draw bars of where there's one wavelength within this wave, and then also indicate how you would measure the amplitude. Go ahead and put those labels in that diagram now. All right, so use your sketch to determine the wavelength of the standing wave. Again, based on this picture and the fact that the wave is whatever length you were assigned at in the Google stream. Mine was 3.6 meters, yours will be slightly different. Figure out what that wavelength is. So you're going to start with that length of the spring, and then you're going to multiply or divide, or, well, it's multiply or divide by something to give you what the wavelength is. You could figure it out from the picture, or if you're not sure, go back in your notes and look up how to determine the wavelength of the third harmonic from the spring length. Go ahead and do that now. Once again, we're going to figure out what the frequency is from this period, and that is, there's a formula between frequency and period. You'll write it out here. You'll plug in what the period is, and then ultimately solve for the frequency. Go ahead and do that now, the frequency based on that period number. Once again, you're going to look up the formula for among V, wavelength, and frequency to calculate frequency again. We got it here. We want to calculate it with this formula and see how these values compare. So you're going to write out the formula that relates these three variables. You're going to plug in the values. What values? This, again, is page 1. You calculated the speed of the wave on the spring. The wavelength is right here. This is what you're solving for. So go ahead, write the formula, put the numbers in, and then solve for frequency. Go ahead and do that now. Last thing, percent error. So percent error, once again, this is the experiment. This is the theoretical. So percent error is the theoretical value minus the experimental value over the theoretical value times 100%. Again, you don't have to write this formula out. Just put in the numbers in this pattern and punch in a calculator to get your percent error. Go ahead and do that now. All right, well, the next thing, now we got all the harmonics done, all the analysis done with all our data. We're going to move on to the questions. So the first question, sketch the following harmonics and determine the wavelength in each of the cases assuming the same size spring used in this lab. So mine was 3.6 meters. You're going to look up what yours is, what you were assigned from the previous pages. Sketch what the fourth harmonic would look like if you snapped the picture. Fourth harmonic. Not necessary to label the nodes, antinodes. You don't have to do that. Just the way the spring would look if you snap a picture of it. So go ahead and make that sketch now. Then what I want you to do is calculate what the wavelength of that spring is based on that the spring is 3.6 meters long. What's the wavelength of that in the fourth harmonic? Go ahead and do that now. The next exercise is to sketch the fifth harmonic. Go ahead and sketch what the fifth harmonic would look like if this were the spring and you snapped a picture of it in the fifth harmonic. Go ahead and do that now. Calculate what the wavelength should be based on the length of the spring here and the harmonics, what's happening. Go ahead and calculate the wavelength now in the fifth harmonic. All right, number 2. Neil Young strikes his guitar string and it vibrates at a frequency of 256 hertz. If he places his finger on the string, shortening it to a length of 1/8 the original, what frequency does the string vibrate at? This is basic guitar playing. When you shorten the string, does the frequency go up or down? Do the notes get higher or lower? Well, you might know, and you might just know from that. But also from the formula that relates V, lambda, and F, you could see what happens to this when the frequency gets shorter. What happens to the frequency based on the formula. Go ahead and do that now and put some answer, a numerical answer of some number of hertz. Go ahead and do that now. All right, moving on to step 3, or question 3. An octave higher than a note in music is defined as twice the frequency of the original note. The first sketch shows the spring vibrating in the fundamental frequency. Draw the next 2 octaves as vibrational modes of the spring. So 1 octave higher, remember, the frequency is doubling here. What does the spring look like? No need to label nodes and antinodes. Just sketch what the spring looks like, or the string, if you were to snap a picture of it. Oops, twice the frequency. 2 times F. I don't know what I'm writing. Okay, there we go. Next thing, draw 2 octaves higher. So 1 octave higher is right here. What's yet another octave higher after that? Sketch what that string would look like if you snapped the picture. Go ahead and sketch it now. And the last question, 4, describe the 2 ways that standing waves are created. Basically, if you're not sure, I didn't talk about it in the lab, go back to your notes and read, if you don't remember, and answer how the 2 ways you can create a standing wave. So that's our standing waves lab. I hope you enjoyed the view up on the ceiling. I hope you enjoyed the analysis, the physics. I'll see you in the next physics video.